Linear systems and matrices. The title of this class suggested already that we're starting to get deeper and deeper into linear algebra territory. You may have heard about matrices before, and in fact they're going to be providing us with a lot of food for thought and food for the development of new methods. But they're going to come up as a necessary tool, or in fact a very efficient tool, from the idea of solving linear systems, or from the problem of solving linear system. So you may remember from the last class that we do have a method for solving a linear system, namely substitution or elimination by substitution. But it is a long method, and in fact we already asked, is there a better way? So in other words, how can we change the given system to a simpler equivalent one? Remember, that was the key to solving a system. At each step we're changing our system to a different one, which hopefully is simpler. So how can we do that in a way that requires simple and effective operations? So rather than having to do all this long method of going up and down using the variables one direction and then the other and so on. So this is what we're going to be looking at in this class. Now, first of all, in order to get to where we want to go, we need to notice one simple but very important fact, and that is the following. There are three types of steps that we can do on a linear system in order to change it into a simpler equivalent one, and these are the following. First of all, what we can do, you can switch two equations. Now in the example you have in front of you, I have the first and the second equation. If I switch their position, of course the system doesn't change at all, right? All it changes is where we're putting those equations. Well, this turns out to be a very simple observation, but one that turns out to be very effective. The other one is, what we can do is we can multiply an equation by a non-zero scalar. For instance, I can take that third equation and multiply everything by some number k. As long as the number k is not zero, what I end up with is an equation which is exactly the same as the one before, only with bigger or smaller coefficients depending on what k is. So this is going to not affect the system in any way, meaning it's going to change it to an equivalent one. Finally, what we can do is we can add to one equation a multiple of another one. For instance, what I can do is, instead of using the first equation as is, I'm going to change it to the equation obtained by adding it to the multiple I just constructed of the third equation. If you do the algebra on that, so if you add the first equation and the last equation as you see them now, you end up with this new, no longer looking equation, which really has the same solutions, the same properties as the old one, in the context, of course, of the system. It's a different equation, but it has the same solutions within the system as the previous set of equations. So it turns out that these steps, first of all, they're called elementary operations. Well, why? Because they're very simple to do. Okay, so they're very simple, basic steps. But they're elementary also for another reason, in that they are the building blocks of what turns out to be the solution method for the system. In fact, it turns out that any system can be solved by using only elementary operations. Now, this may look like a very tall claim. Is it true that I can actually take any linear system whatsoever, whatever many equations, whatever many variables, and just using a combination of those three types of operations, I can solve it? Yes, it is true. The formal proof is actually rather tedious, so we're not going to look at it. And in fact, it's not very inspiring and not very convincing anyway. Instead, we're going to prove it by checking that the proof, as they say, is in the pudding, and showing you in fact how that is done.